let's see what happens when you're dealing with multiple lenses, not just a single one. So one of the major concepts is that the image of the object that's formed in the first lens is going to become the object for the second lens. So if I draw this here, let's say that we have the first lens and the second lens, and we place an object here. That object might form, I don't know, I'm making up a drawing here, an image right here. So this is object 1, this is image 1. And this image becomes the object for the second lens. So now we're going to make up a drawing for this one and see that the final image is going to be here. So this is image 1, which equals object 2. Again, let's look at it one more time. So the object will form an image for the first lens, and the image will be somewhere here. Then the image becomes the object for the second lens and forms a final image somewhere here. Now, where the images are formed depends on the separation of the lenses, depends on the focal length of both of the lenses. So it's possible that this object has an image somewhere there, and then this becomes a virtual object for the second lens. So there's many different situations that this can happen. We can work them out more easily mathematically, but the concept that I'm trying to discuss here is the fact that the object in the first lens makes an image. This image becomes the object for the second lens, and that forms an image. The second concept is that the magnification of the final image is a product of the magnifications in the two different lenses. So let's say that we have a magnification M1 in the first lens and a magnification M2 in the second lens, then M is going to be M1 times M2. And it all comes from the height final divided by height original, where you have to take into account two different steps for height final through the second lens, height original through the first lens. It's just a matter of manipulating math equations, and you can see that that's the case. So let's look at an actual problem now. So say we have two lenses of focal lengths 3 centimeters and 5 centimeters, separated by a distance of 8 centimeters. Let the first lens be diverging and the second to the right of it converging. If we place an object 8 centimeters to the left of the diverging lens, where is the final image with respect to the converging lens? Is the final image upright or inverted? And what is the magnification of the final image? Let's start by drawing a diagram of what's going on. So I'm going to have a diverging lens first, followed by a converging lens. And we are told that this separation between the lenses, I'll call it X, is 8 centimeters. We're also told that the focal length of the diverging lens is 3 centimeters, and for the converging lens is 5 centimeters. So this point is the focal length of the diverging lens, but it's also the focal point of the converging lens. It's just an accident in the numbers that I picked. Then we're going to place an object 8 centimeters in front of the diverging lens. So I'm going to also write down our knowns. So I'll put them right here. So we have focal length 1 is 3 centimeters. Let's stop and think. We're given a positive value for focal length 1, but we know that the first lens is actually a diverging lens. So that makes the focal length negative. Okay? Then focal length 2 for the converging lens is 5 centimeters. And since it's converging, the focal length should be positive. Then the two lenses are separated by a distance x of 8 centimeters. Then we have an object placed 8 centimeters in front of the diverging lens, and the unknowns are the final location. So I'm going to call this D image 2. So the distance from the second lens to the final image. In part B, we want to know if it's upright or inverted. In part C, we're looking for the magnification of the final image. So let's start working through this. We know that the original object is going to form an image in the diverging lens. Remember that diverging lenses only form virtual images. So the image is going to be somewhere in front of the diverging lens. Let's see what happens when we use the math. So 1 over f1 is 1 over do1 plus 1 over di1. That means that di1 is 1 over f1 minus 1 over do1 to the negative 1. So di1 is going to be 1 over negative 3 minus 1 over 8 to the negative 1. And if we plug in the numbers, we get negative 2.2 centimeters. Let's stop and think. So we have a negative sign here for an image distance. So remember that a negative sign for the image distance means that the image is formed on the same side as the object because it's a virtual image. So our image is going to be somewhere here. So this is object 1, this is image 1. So our answer makes sense. It should be negative because it should be in front of the lens. Now, we have to deal with a second lens, and we know that this image is now the object for the second lens. So the object distance will be this entire distance here. So that is the 2.2 we have here plus 8 centimeters. So we're looking for the distance directly from here to there. So let's write that down. So now we have DO2 is 2.2 plus 8 or 10.2 centimeters. We're just strictly looking at the distance away from lens 2. So now we're going to use the second lens, the lens equation. 1 over f2 is 1 over do2 plus 1 over di2. So we're solving for di2, and that is 1 over f2 minus 1 over do2 to the negative 1. So that is 1 over focal length 2 is positive 5 minus 1 over do2, which is 10.2 to the negative 1. And when we plug in the numbers, we get 9.8 centimeters. Kind of strange to write 9.8 centimeters instead of 9.8 meters per second squared. But there we have it. So let's figure out if this makes any sense. We are dealing with an object that is farther away than the focal point of this lens. And we know that in that case, it forms an image that is real and on this side of the lens. had the object for the second lens started here inside the focal point, then it would have given us a virtual image. But since it starts to the left of the focal point, it's going to give us a real image, and the positive value for the image distance is going to be correct. All right, so now is this upright or inverted? Well, let's kind of draw here a ray diagram. I'll need a different color. Let's try this one. So I have the beam that's parallel to the principal axis. It's going to pass through the focal point. It's supposed to pass through the focal point. I didn't quite get it. And then the second beam goes through this focus and is bent parallel to the principal axis. So the final image should be here. And the image then will be inverted. Another way of looking at it is to think, well, I started out with an upright image that is going to have I started out with an upright object that will have a real image in the converging lens. So an upright object will give an inverted object going through this converging lens. Let me jot down some other things here. So I said that this was image 1, but it's also object 2. And then this to the right is image 2, or the final image in the problem. Now let's look at the magnification. So for part C, the magnification is magnification through the first lens times magnification through the second lens. So that is negative di1 over do1 times negative di2 over do2. So that is negative di1, that is negative 2.2 centimeters divided by do1, which was 8 centimeters, and then the other one is di2, so that's 9.8 divided by object distance, which was 10.2. So I'm going to just play with the pluses and minuses here. The two minuses here become a plus, so I'm going to leave it as 2.2 divided by 8, and then I have here negative 9.8 divided by 10.2. And the reason I'm doing this is because, remember, this is M1 and this is M2. And M1 should be positive. It's a positive magnification because the image is upright. And M2 should be negative because the image is upside down. So that checks out as well. Now if I plug in the numbers, I end up with a magnification of 0.275 times negative 0.96, or approximately negative 0.264. So our image is going to be upside down. It's going to be inverted because it's negative, and smaller than the original object.